Welcome to part three of volcanoes and igneous processes. In this last part of our discussion, we're going to talk a little bit about volcanic hazards and living with volcanoes. Volcanoes are basically here to stay. In part two, however, we talked a little bit about the types of volcanoes, the shield, the composite, the cinder cone, and how the composition of the uh, volcano itself dictates the type of volcano. We looked at various volcanic features in part two, and then towards the last part of part two, we associated plate tectonic processes in terms of plate boundaries and the composition um, from the plate interaction, creating the different types of volcanoes. So, again, part three, we're going to look at living with volcanoes. So, here are some statistics to start with in terms of how volcanoes impact society or our lives. 10% of the Earth's population is situated near volcanoes. Seattle, Washington, Mexico City, uh, Tokyo, Japan, Naples, Italy, Ecuador. These are all areas of major composite type volcanoes exist and that are active. Volcanoes are destructive as well as unpredictable, very similar to earthquakes. And so, again, we're going to take a look at how volcanoes interact with society with regards to volcanic hazards. So, let's take a look at the ranking of volcanic hazards. And when we look at the ranking, we're looking at probably which are most destructive. And for example, pyroclastic flows, typical of composite volcanoes. Again, as we discussed in part two, we have mixtures of gas, ash, pumice. Temperatures are 800 degrees or more during a pyroclastic type of composite volcanic eruption. Pyroclastic clouds are common. We talked earlier about the newer Adont clouds that emanate from the crater and move down the flanks of the volcano. Layars, which are huge mud flows that move down these pre-existing stream valleys. Again, some of these layars reach up to speeds of 60 miles per hour. There's a potential threat of layars even with an inactive volcano. And later we'll talk a little bit about what causes a layar to show you that even an inactive volcano can be subjected to mud flows. And of course, these areas are highly potential with glaciated volcanic summits. So, in other words, layars are a direct result of volcanoes that are snow capped. Another hazard with volcanoes is the rapid collapse of the crater or areas within the flanks. Creates a rapid mass wasting events, meaning that under the influence of gravity, you can have a lot of movement of material in terms of mudslides, debris slides, and so forth. And then, of course, in terms of volcanic hazards, we can have explosive eruptions, as we discussed in part two of the volcanoes typical of composite volcanoes. And, ash clouds can be felt 100 miles away in any geographical area. In fact, I have a little example down here in my bullet point saying that in 1989, a Boeing 747 nearly crashed because of an eruption of an Alaskan volcano. So, kind of reviewing parts one and parts two of the lecture, we're showing a typical composite type volcano. And here you can see all of the pyroclastic eruptions associated with the composite. Certainly, we talked earlier about material being ejected from the volcano in terms of bombs. Here's a collapsed flank of the volcano, causing possibly some type of mass wasting process, the debris flow, debris slide. Here's a lava dome. Lava dome collapses, again, creating a pyroclastic type flows. Here's the eruption of ash into the atmosphere, the ash fall reacting with processes in the atmosphere, creating acid rain. Here's a newer ardent. Here's the pyroclastic flow that emanates down the flank of the volcano. And so you can see just in this picture, there are numerous geologic volcanic hazards associated with an eruption of a volcano, especially a composite volcano. And at this point, you should be shaking your head. Yes, composite volcanoes, and know the difference between eruptive styles of a composite versus a shield volcano. And just one more mention, here's a layar emanating down the flank of the volcano. So this slide shows a picture of the Seattle area in the northwestern part of Washington State. If you've ever been to Seattle, I think it's one of the most prettiest cities I've ever been in. It's a beautiful city. But Seattle is basically constructed on a series of old or ancient layars. And a layar, as we pointed out in discussion part one, a layar basically is a huge mud flow that results from the heating of magma, or the magma rising and heating the top of the volcano, melting the snow, and then the snow, of course, turns into water and runs down pre-existing stream valleys and collects everything and anything. And as it gets to the base of the mountain, it deposits itself into these big, thick sequences of basically mud. And this is a picture that shows a map of old layar deposits in the Seattle area. And so where my arrow is at the bottom right-hand part of the diagram, you see Mount Rainier, which actually today is an active stratocomposite volcano in Washington State. And you can see where these black areas are pre-existing stream valleys in which, over geologic time, before Seattle was built, these were ancient layars that have migrated and moved down the flanks of the Mount Rainier volcano and deposited these thick sequences of mud flows in the lower areas of the Seattle. So here's Renton, here's Kent, Auburn. These are all sub areas of Seattle, Puyallup, and so forth. And these are areas in which the city of Seattle itself has been built on ancient layars, which begs the question in terms of a geologic hazard. What would stop Mount Rainier from producing future layars that basically would emanate down these stream valleys and actually bury the city of Seattle? And the answer to that question is nothing. There's no reason why that would not happen. And so folks who study geologic hazards and are watching Mount Rainier very closely, watching for the detection of the magma moving towards the top of the mountain, again, activating or melting the snow on the top, causing a layar. So this is a very important area to watch geologically for hazards with respect to layars in the Seattle area. This is a picture of Seattle. You see the Space Needle to the right, and you see Mount Rainier in the background. You can see Mount Rainier having the characteristics of a typical strata composite, felsic composition, very explosive type volcano. And again, even today, Mount Rainier is very active. Very beautiful, though, in the skyline. You don't want to make this volcano mad. So monitoring volcanic activity. So what does a geologist do with respect to working in the geologic hazard area of geology and working with volcanoes? So monitoring volcanic activity is really typically measured by observing the movement of magma. So the movement of magma up the volcanic conduit or the neck is an indication that the volcano is active and could be erupting. So geologists, hazard geologists, measure the frequency of volcanic earthquakes. That's an indication that the magma is making its way up towards the top of the volcano, because when you get big voluminous amounts of dense rock material beginning to move, it's going to shake things up. So earthquakes are one indication of a volcanic eruption. Volcanoes that have historically erupted in the past are equipped with seismographs, And so Mount St. Helens, Mount Rainier, some other volcanoes along the Cascade Range in the United States have seismographs that are constantly monitoring their frequency of movement or frequency of earthquakes. An increased volcanic earthquakes, typically an increase of earthquakes in a volcano is could be, and typically it's a precursor to an eruption. So again, monitoring that magma going up the conduit is very important. Expansion of the magma chamber, changing the size and volcanic of the topography. So the size of the volcano is monitored. There's instruments, lasered instruments that can watch the size of the volcano with respect to its flanks and the top of the volcano, because rising magma certainly, as it moves up the conduit, can build the volcano, can prove as a precursor, meaning that if the topography or the size or shape of the volcano begins to change, that is a huge indication of a possible eruption taking place. So frequency of earthquakes and monitoring the size and shape of the volcano are important with respect to predicting a volcano eruption. And so here's just a picture of a person, if you look at the lower part of your screen, with some laser instrumentation, watching and measuring the shape and size of the volcano. Changes in the pre-eruptive volcanic gases. So certainly a sign of a possible eruption is the increase in sulfur dioxide gas emissions. And certainly sulfur dioxide smells like rotten eggs. And so because we know that volatiles are less dense than the magma itself, so typically gas emissions are going to come out of the volcano prior to a major eruption. Again, it's like a soda can. The gases collect at the top of the can, and when you release that can, the gases come out first. Another part of monitoring volcanic activity is increases in ground temperature, surface temperatures. Again, it's all related to the rising magma in the conduit. And as magma rises, surface temperatures rise, radiation of heat, again, from that ascending magma. And so again, this is a person looking at the South Sister volcano in the Cascade Range in Oregon. And then here is an example of a volcano, composite volcano, I'm assuming because of the ash cloud that's developed in the upper part of the atmosphere, the troposphere. And you can see it from space. And it looks like the picture I have next to it is a boot kicking an island. Well, we should all recognize that that looks like the southern portion of Italy and the island of Sicily, where this particular volcanic eruption has taken place. So really, a volcano isn't really a hazard until you get more and more people living around the volcano, because volcanoes have been erupting since the beginning of Earth. And so in terms of geologic hazards and in terms of population, we would suspect to see more and more geologic hazards with volcanoes with the increased population of the world. So the more and more people that reside on the Earth, consequently, the more and more people are going to live next to volcanoes, and then now volcanoes become more of a geologic hazard.